Welcome to the workshop. Today we want to take a look at section 4.2, paths and circuits. And before we get into the paths and circuits themselves, we want to expand our graphs, our collection of graphs. And we want to do that by considering an expansion of our definition. So let's take a look at our notes. Now, we said that our definition of a graph G is a collection of, let's see here, vertices and edges. Okay, so the vertices is a set, and the edges are a set of subsets. Now, when it comes to sets, if I were to say, for example, the set A, B, C, D, this is equal to the set A, B, C, C, D, B. As sets, these are the same thing because A are the same thing, B are the same thing. They're not distinct from one another. So in our definition of sets, right, A is only one thing. They're not distinct from one another in general. However, if we say to ourselves multisets, and the reason that we want to talk about sets as these not being distinct from one another is because if I talk about the two-element subset A, D, which A am I referring to? And so this in general is a these two sets would be considered the same thing. Now, if we talk about multisets, multisets do allow for repeated elements. So let's, right, and multisets, these would not be the same thing. However, we want to consider it in terms of sets and two-element subsets. So let's consider again A, B, C, D. If those are my vertices, I could look at the set of edges having A, B. And for the expansion of our definition of graphs, we want to allow for repeated two-element subsets. So while we're not going to repeat vertices, it'll still be A, B, C, D, our two-element subsets will allow for repetitions and will allow for repeated elements in the two-element subsets. Okay, so allowing for these sorts of things expands our definition of graphs. So to be clear, if it wasn't clear before, we should not see this sort of thing in a graph. Okay, this is raw definition here. But in a multigraph, these things are okay. So multisets allow for a multigraph, and that's what we want to expand our definition of a graph to. So a multigraph consists of a non-empty finite set of vertices, same thing as we had before for a graph, and a set of edges. Okay, so that in and of itself is no different than a graph, but the extension here is we allow an edge to join a vertex to itself. So we allow these sorts of things, or to a different vertex. Okay, so of course you can attach it to anything, another vertex, so itself or another vertex, and where we allow multiple edges joining the same pair of vertices, right? That's this situation. We're repeating the two-element subsets. So again, how is that different from a graph? The repeated edges are not allowed in a graph, and the repeated vertices for a given edge is not allowed in a graph. In a multigraph, these things are allowed. All right, so an edge from a vertex to itself is called a loop. And when we have two edges between the same pair of graphs, those edges are called parallel. So to solidify this, let's take a look at a quick example. Let's identify the loops and the parallel edges in this graph. excuse me. So we can see edge B and edge A are parallel. So edges A and B are parallel. We can see that edges I and J are parallel. And we can see that edge M is a loop. So A and B go between the same pair of vertices, U and V. I and J go between the same pair of vertices, Z and Y. M connects the vertex W to itself. So that's parallel edges and loops. Now, you'll notice, or hopefully you noticed, that what we have is a little bit different than what we saw in the previous section discussing graphs. In particular, these edges are labeled as well. In the previous section, we just had the vertices labeled. Here, the edges are also labeled. And the reason that we do that is because we have multiple edges representing the connection between two vertices. Edge A and edge B are both represented as U comma V in the edge set. So we label them separately so that way we can refer to them as two separate edges, right? If I refer to the edge connecting U to V, you wouldn't know which one I'm talking about. But if I say edge A, of course. So that's why we have the edges labeled, which helps. So that's just an FYI, just trying to keep up with notation here, what kind of things are labeled. So we have the vertices are labeled with capital letters, the edges are labeled with lowercase letters. And that will be the standard used throughout this text, I believe. So, or we'll try to keep that. I suppose there is the situation, some of our examples come from other textbooks and or are generated by me, and some of those may look a little bit different. But when you see examples like this, it should be clear as to which are vertices and which are edges, and it should be consistent. So in this case, capital letters refer to vertices, while lowercase letters refer to edges. All right. So one last thing that we need to consider with this introduction of multigraphs, we should also think about how that changes what we're looking at for the degrees of our vertices. So how does the adding of the edges change our counting of degrees? Because previously what we said was we're just looking at the number of, let's see here. Well, depending on your definition, I don't remember which we used exactly. The degree of a vertex can be described as the number of adjacent vertices. And if that's the case, then the degree of U would simply be 1, 2, 3, because V, X, and R are the adjacent vertices. However, that's a definition that really is referring to graphs. Excuse me. Here in multigraphs, we want to think of it more as how many edges are incident to the vertex. So for vertex U, we have A, B, N, and G are incident edges to vertex U. So the degree of vertex U in this case is actually 1, 2, 3, 4. So that's pretty straightforward. Let's see, so we've calculated the degree of U. Let's also look at X. X is no different, right? There's no multiple edges, there's no loops, or there's no parallel edges rather, and there's no loops. So it's just the 1, 2, 3, 4. And it doesn't matter which way you use to count it here, because this doesn't have the situation of the multigraph. It doesn't have the parallel edges, it doesn't have a loop. So there's nothing new or special about this. Adjacent vertices, 4 of them, or incident edges, 4 of them. So the degree of vertex X is also 4. Now, what about vertex W, the last one that we want to consider? The degree of vertex W, if we talk about the incident edges, then we're talking about C, P, D, and M. But what's weird is there's a loop. M is a loop. So does that do different? Does that act any differently in the counting of edges? Yes. A loop will actually count twice. So in its most basic sense, if you want to count the degree of a vertex, all you do is look at how many things are attached to it, ignoring where those things go. So we've got 1, 2, 3, 4, 5. I don't care that those are attached. I've got 1, 2, 3, 4, 5 ends of an edge. 5. So it's a little bit right. The exact description of how to count the degree of a vertex is you could say it's a little bit difficult because the rules maybe aren't clear, or there's a lot of rules, right? If you think of it as adjacent vertices, that doesn't work when you talk about parallel edges and loops. So we can't use that. If we talk about incident edges, that works for parallels, no worries, or a regular graph, no worries, but then we have to give it an additional rule saying that loops count twice. And so that's perfectly acceptable. So count the number of incident edges, loops count twice. Or you could simply say, how many ends of an edge do I have? Well, this loop has 2 ends and they're both attached to W. So that's 1, 2, 3, 4, 5. Maybe a little bit more straightforward. But either way, you think about it, these are the numbers that we should be getting. So that's all that I wanted to introduce for now. So the idea of a multigraph having parallel edges and loops. Awesome. The definitions that we'll talk about in this section allow for multigraphs. So we want to make sure that we know what a multigraph is before we get there. So I'll see you guys back in the workshop very shortly, continuing on in section 4.2.